Hi, everyone. Thanks for that introduction. So today we're going to talk about the science productivity and hopefully how we could leverage some of the things that we're measuring about programmers to make them more effective at their jobs, right? If you're not a programmer, if you don't do software development, I think you could still take something out of this talk because it really just reflects on how do we become more productive, or what are some of the things that limit us from doing that. So that said, let's get started with the activity here. Spend about 1-2 minutes talking with people next to you, like you two talk to each other. Just what makes you most unproductive? You know, maybe it's email, Facebook, I don't know. What was unproductive for me has changed based on what my job was. When I was a software developer, I was in industry for about 10 years, full-time as I was going through school. Interruptions was a big part of what made me unproductive, right? So we would be asked to work, but then we have a meeting to go to. Like, when I'm doing something, I don't want to meet right now, but okay, I have to stop my work, go to a meeting. Or you're in these big teams of people and they're asking you questions, and it's hard to ever get focused, right? Because especially as you get more senior, people want to ask more and more questions. So every time you try getting involved, you get interrupted more often, right? So you're kind of a bottleneck for knowledge. You find that programmers, for example, will often work at night because they just can't work during the daytime because they find too much interruptions, right? As a professor, I find my biggest source of unproductivity is fragmentation. So it's not that I don't have time to do stuff, it's that I have it sliced and diced in very small chunks. So for example, maybe I have 3 hours in the day to do something, except that it's like 10 minutes in between these two meetings, another 30 minutes in the afternoon, and 30 minutes kind of after dinner, right? It's kind of so sliced and diced that I can't do these big type of tasks that I used to do, this deep work where I can kind of just absorb myself and work for 4 hours at a time on something, right? I have to figure out how do I do the same work in a very small time, right? That's been a big problem. Some other things I've heard is task fatigue, or motivation. So you just don't want to go work on something, or you're just like, you try doing it and you just feel tired instantly. As soon as you open up the homework assignment or project that you're working on, you don't want to do it. Another big problem I've seen is slow feedback. So in programming especially, or just even with you working with other people, where if you, for example, it used to be if you build something in software, it would take several hours for it to compile, right? And that was a slow feedback loop. So, 3 hours later, find out, it doesn't work. And then you try again, right? Or if it's hard to test in production because you have to set up all this database stuff, it's hard just to get feedback, does this work, right? When you work with electronic devices, that's a big problem, right? It's hard to set up all these things. When you work with people where you have to go through a lot of processing, like testing, QA, there's a lot of silos, then that's a slow feedback because you get something back 2 weeks later that, this is a problem, right? And so that slow feedback is often a problem. So we have all sorts of productivity strategies. Okay, so the time boxing is the keyword, and that it's that you work for a set amount of time, and you build in some time to kind of relax. So I think by default, they say something like 25 minutes on, 5-minute rest, and then 25 minutes on, and so on, right? So that's one technique. There's something that I have done before, but I'm not the only one I've heard of doing something like this, is I do what I call like task paths. So you go around and work on one task in one location, right? So you go to a coffee shop and you work on something, and then when you're done, you work for an hour, and you need to work onto another task. There's somehow you just don't feel motivated to do that. But if you go to another location, by the time you walk and had time to kind of stress it, get somewhere new, you could work on that new task, right? And so it's a way to kind of do something like that. Another technique, self-sourcing. So if you ever heard of microtasking, like Mechanical Turk, where you could say, you have 1,000 photos that you want to label. You don't want to label 1,000 photos, but you can send them out to someone. So that's crowdsourcing. But self-sourcing is where you do the same thing for your own task. So you say, well, I don't feel like cataloging all my travel photo trips in one day, but I'll do five right now. And I'll just do 5 a day until I'm done, right? So you have this way of making all your tasks these very micro tasks, right? So that's one technique. Some people do things that block out other stuff, like headphones. I wear headphones and it puts me in another mental state. I block out other stuff. Even if there's no music sometimes, you just do it. There's all these techniques. If you've ever read Lifehacker, it's like there's countless suggestions on what to do. One example from Martin Twain, writer in the 1800s, he said, "Eat your frog in the morning." What does that mean? Sounds kind of gross. He basically means do the task you want to do least in the morning when you have the most energy. That's kind of the philosophy there, right? So eat your frog, the most unpleasant thing you can think of, do that in the morning, do that first, right? There's kind of a newer thing now. So one thing I'm wearing right now is a Fitbit, right? Anyone have something like that, or at least seen some of this? So you could do these things with your phone too. So you could go running and you could say, today you ran 2 miles, and you beat your best from last time, right? So if you kind of track all your behaviors, you could start having feedback about whether you're making progress. So the metrics themselves, and often competing with other people, could be kind of a productivity strategy, right? So what's the problem with all of these things? Is they're all unscientific, right? They're all these random people telling you, like, this is no different than when people would say, if you want to cure something, you get a leash and suck your blood out, right? We don't really know, are these more effective than other things, right? And so my big challenge has been, how can I start taking some of these kind of suggestions and some other things that people do, maybe tools that we can build, I'm focusing on programmers, that would help them become more productive, and how can we know that it works, right? All right, so just to get into the mind of, let's do kind of like the same thing, about a minute, just thinking about what makes programming hard, right? So, let me give you an example of why I think programming is very interesting. I'm gonna show you 2 different graphs, and I want you to guess which graph is from a programmer and which one is from a typical office worker. So you can say the top one or the bottom one. Who thinks the top one is from a programmer? Okay, a couple people. Who thinks the bottom one is from the programmer? Okay, a lot of other people. Okay, it is the bottom one. This is what I think makes programming so interesting to me, because it's the intensity of which you have to do your work, right? The top one is an example of your typical office worker, an accountant, someone that is working with Excel spreadsheets all day long, doing other kind of office administration tasks. You basically can, if you had some way of measuring their productivity, basically what you see over time is they start off fresh in the morning and then just depletes over time. You do not see that with programmers, right? With programmers, what you see are these incredible bursts of energy where they just work for crazy long periods of time on something very intense, right? So this session down there that's about a 5-hour nonstop just work. They're just typing and doing stuff, right? That's insane, right? There's very few other professions that do that. In kind of the arts, you kind of do that. Some other disciplines, you do have this very kind of creative process. But what's interesting about that is you kind of have that creativity mixed in with the engineering aspect, right? And the fact that you have to keep all these things in mind is what makes programming so intense, right? So when we look at just some basic stats, like any time a programmer stops work, even just for like a minute, it often takes them 10 to 15 minutes just to rebuild that context to get back into work. And it's 90% of the time. So if you had someone, for example, ask you a question and you go back to work, only 10% of the time do they actually get back to it in a minute. So if they say, this is just a minute, can I ask you something? Well, that's only true 10% of the time. The rest of the time, they blow their context. And work fragmentation is a huge problem. So they basically very rarely get this type of 5-hour session to work What it really looks like in practice is you see those little humps there on the far most right. They have like about 5 or 6 of those. That's how most of their work is done. They do these little chunks of time, and they spend about 30% of those just recovering all the time, right? So this is a big problem that people have. In my dissertation work, we did this really intense study on interruptions. We built some tools that help people get back to speed. But what I want to kind of show is just some stuff beyond that, right? So one thing that we might want to be able to do is, say, given we have all that history of people, we want to be able to ask a question like, how could we look at people's work patterns and make general recommendations? So if we say that your Mondays are your least productive days, you have a way of being able to say, well, it's because you have a really bad meeting, or you're just doing, you're not devoting enough time to work in a long enough stretch, right, to get your work done. So being able to make those sort of recommendations is something that we can't do right now. But given the data, this is a very likely future, right? So this is one way that we could make people more productive. But I think this is a pretty low-hanging fruit. I think we could do more interesting stuff. So one thing that we looked at, just as an example, is we asked a little bit more specific about interruptions as we looked at context switching. So just to give an example from the audience, what's one type of context switching you might do? Anyone having it? What's one type of context switch? How many people have taken 2 classes, right, or 2 projects? Then that's a context switch, having to go back and forth between, right? So there's this theory put out by Jerry Weinberg that basically talked about the limits of how many projects you could take on simply because of context switching. So he suggested that each switch from one project to another would consume 10% waste. So if you had, say, 3 projects, just to be able to switch back and forth between them even just once would basically eat up 40% of your time, right? So you basically have this kind of hard limit of how much work you could do simultaneously before most of it gets eaten up by context switching, right? On the other hand, we actually, and so we could think of different types of context switching, like switching between projects, but what about lower level ones? Switching between files, switching between different types of tasks, like I'm debugging something, editing. And another slide. Okay, I think it's just missing a picture. So what I wanted to say about this part is, but on the other hand, we have this theory of, we know that people can actually take on 2 tasks at once if they're kind of not competing with the same resources. So there's actually studies that show that the brain can split into 2 different hemispheres and take on 2 simultaneous tasks if they do not require the same type of process. So if I'm doing a motor visual task and a language type of task, I could do these at the same time because they don't access the same task. If they're really simple tasks, then there's enough kind of mental buffer for each hemisphere to be able to do this simultaneously. So it could be possible that we could do lightweight context switching. So if we had to do kind of switch from one thing to the other, it's probably okay. And in fact, we know most people do this. Most people do a micro context switching, where you're kind of listening to a talk, checking your email, thinking about what you're going to eat for lunch, and then looking at the talk again. Or when you're programming, you'll even kind of switch and kind of rapidly go to your music player. And you're doing this within a couple minutes, right? You're not like making this really big context switch. You're doing these mini ones. And we seem to do okay with that. So the real question is, given all these types of context switching, which ones are most expensive? And so like the simplest one you can think of is, say I was doing some like unit testing, and I'm doing a web Selenium driver to test out my web page, but then I need to go to my services and my databases part of the code to make some changes as I'm doing this, right? So you can think of each file switch as kind of a lightweight context switch, but it could be a little bit more expensive, right? So if I had to switch components, say from a unit test to where my database is, that's kind of conceptually a bigger jump, right? Because I am just working with completely different types of artifacts, and they're just different mental models I have to load in. So perhaps that's going to be more destructive, right? And so we've actually done an interesting analysis of where we have like about 300 programmers where we're looking at their context switches. And we actually recently added projects, which we don't include here. And we're actually able to show some interesting stuff. So we could see that file switching actually isn't a you could still have very high productive programming sessions with file switches. But as soon as those file switches are actually switches between different components or namespaces, they become more expensive. So you could see that if you're switching between two files that happen to be in the same kind of conceptual location, that's okay. But as far as you doing more expensive conceptual leaps, the context switches become more expensive, right? And most expensive of all is state switching. So if you have to switch from building your program to editing to debugging, that has the most expensive context switch, right? But so it's cool that we can kind of get a really basic insight like that. But how can we go deeper, right? So we didn't really investigate anything about what are the mechanisms of productivity. So next I'm going to explain some brain imaging studies that we've been doing to kind of really see what happens when you do all this sort of stuff, right? And this gets pretty deep. Right. So one of the techniques we looked at is functional magnetic resonance imaging. And basically, it gives us a way to really see what happens in people's heads. So when we say something like, does one type of task make you have higher cognitive load than another, we can start answering questions like that. If we give you this tool or this type of programming language, does it make people able to have less things in their head? We can measure that. We could see it in these scanners. And we'll go into some of the details here. Given all the other choices, there are other ways of measuring brain activity. We could go down to the actual neuron level. There are studies where they actually, when people have to do surgery, they'll put ECOG onto the surface of the brain, and they actually will measure very high fidelity signals about the brain. There are things that use chemicals to actually be able to see the actual neurotransmitters that are activated. So you could see things like whether someone is activating a memory, forming a memory. You can see it at that level because you can see the actual neurotransmitters that get activated. The main thing you're trading off between is this amount, how fine of an area you can target in the brain versus how long of a period that you look at. So for example, PET allows you to see what parts of the brain are activated, but they tend to happen at slower periods of time. EEG is really good. You can know exactly when something happened in the brain, you just don't know where it happened, right? Right. So at a high level, how does fMRI work? So it's pretty simple. Normally, your brain has a whole bunch of like oxygen molecules that are all just randomly doing stuff. When you go in a big giant scanner, they will all kind of align along these fields. And what you can do is you can basically send a radio wave that will cause these certain atoms to bounce. And you can measure the time it took for them to come back, right? Right, so you kind of see that. And there's a little twist here. So when you think really hard about something, when you're looking at some code that's really hard, it's going to consume it's going to need some oxygen to kind of replenish. You need more blood supply to deliver more oxygen to all your neurons, and you'll see that. And what happens is that those neurons, or that area of the brain, that doesn't have blood, that are depleted, becomes more magnetized. And essentially, they become slightly more tilted, right? And so you have a way of telling the difference between parts of the brain that have more blood that was recently added versus ones that don't have more oxygen added, right? Okay, so what does this typically involve? So you get in this big giant machine. It's very noisy. You have like these kind of like headphones that like you would wear on the airport runway, like because it's very loud. And you're looking at this code snippet. We can see what parts of the brains are activated, and we can respond to how people think. But it's not as easy as that, right? There's a couple things. One, when you're looking, oh, I'm so sorry. When you're in that scanner, you're actually looking. You could wear goggles, but more commonly, you're looking at a mirror that reflects the computer screen that's outside, because you can't have things that are metal in there, right? So you're looking at these little code snippets in a mirror. The other problem is, as I'm looking at, say, this code snippet, I am activating lots of parts of my brain, right? So you basically, if you were just to look at brain activity in itself, you would just see it's pretty much on, right? It's not telling you what you want to hear. What you typically have to do is you have to identify a control condition to kind of subtract out what parts of the brains you want to narrow in on. So typically what will happen is you want to look at what people do when they're resting, kind of a normal, relaxed state. You want to look in a condition that is very close to your task under study, and then you want to look for the actual task you're interested in. In our case, what we did was we wanted to know what it was like to even comprehend a piece of code, right? And so what we did was we took two tasks. We took one where we asked people just to look for syntax errors, and then we asked people in the other task to look for, or to calculate the value of the return value, or ask for calculation for part of that code, right? So the thing you can do with syntax error is you have all the same types of actions that you would do typically with looking at code. Your eyes are moving around, you're kind of looking at basic syntax, but you're not doing this higher order of thinking about things, right? So it allows us to see kind of that baseline and subtract out all those kind of common things that aren't really under interest to us, right? And so if we look at that delta, it creates this very small area. So you get to see that, all right? So if we look at the timeline, you basically have where they're starting this activity, and you can kind of see this oxygen curve over time. And we can use this to model what parts of the brains are activated, and compare each parts of the timeline of that to each other. So this is giving you an example of what this would look like. So please understand this code snippet. Like, what is the output? Look for the syntax error, right? And you would have, say, a minute to do this, right? So imagine you're in this really loud thing, and this is going on. This is what you're looking at. It's actually very common in psychology studies to fall asleep. I've had that when I would volunteer to these things. You just fall asleep in it because you're asked to look at hundreds of things. You sometimes fall asleep. So we didn't have too much of a problem with the coding. And what you would typically get is we would want to look at all participants, and we would want to do some basic things like motion correction if people moved around. We have to do a little bit of transformations because people have different skulls and brain areas. So we have a way of mapping to a standard brain. Yeah, and there's kind of a standard way of doing a transform on the brain so that we always get a corrected image. Okay. All right, but then what this starts to do is it allows us to actually see what parts of the brain are activated by something, right? And we could do is we could map this to existing cognitive processes that we know that other people do, and be able to start saying things like, what is it exactly that people need to have in their mind when they're understanding code? So we can actually tell when people are, for example, silently reading code. So we can actually see that they're actually reading words aloud, and we know exactly when they're doing it. We know that they're using their grammar networks to kind of comprehend the snippets. And where this gets really interesting is a lot of people think that coding is related to mathematics. Like they say that it's basically a mathematical operations that you're doing. If you have for loops, if we're calculating the median in something, this is all a mathematical thing you're doing. It turns out that once you're experienced enough in programming, you've abstracted the process so much that as soon as you see these kind of code blocks, you instantly think it like a second language, right? You're bypassing any sort of calculation. You're treating it just like grammar, which makes it very different than other type of reasoning processes. There's lots of tasks where you do these logical comparisons, like, you know, Susan is someone's mother, are they each other's aunts? You know, like those sort of logical tasks, any sort of kind of like problem solving sort of thing, these, you can see that people are having to divide attention between things and use very similar problem solving, right? So that gives us an idea. And so I just want to give you some other examples of stuff we're looking at. So for example, we know the difference between an expert and a novice in lots of tasks is about how much parts of the brain they activate to do something, right? So basically the way the brain works is it's very expensive to activate lots of parts of your brain, right? Because you're using up energy and you have to eat more food and you're not going to survive, right? And so experts learn how to minimally activate their brain. And they find in studies of where you look at people like, say, expert golfers, what they end up having to do is they have to, if you look at a novice golfer, I've never golfed before, you kind of have to think about everything, every single detail. So you're just kind of like, I have a club in my hand, where did I put it? Where did I put my knees? Like, you have all those sort of details in your mind. And you can see that. That's actually the activation on the left is a novice golfer versus an expert golfer has encoded the act of golfing into a single motor area response. This is all they activate. That's it. And it just gets done, right? And they've learned to do that. We're starting to do studies of programmers to see which areas make it, where do expertise show up? What parts of the brain are really important for programmers? So we have other examples. Taxi drivers, for example, they have larger parahippocampuses because they have all these, they have to exercise a lot of spatial memory, right? Video game experts like that do contests and stuff have larger, basically visual spatial areas, right? Because they practice that. What is that for a programmer? We don't know yet, but we're getting there. We're looking at, in this study, we're able to start getting an idea of we're able to start seeing the effect of more complex code. So we actually looked at data that would happen during the rest period. We noticed that when we had these metrics that calculated how complex the code was, that there was this increased activation in these areas. And we're starting to think that this is either people reflecting on the task, so you could start detecting when people need more time to process something, or this potentially could even be signs of people starting to enter their flow state. So one big goal would be able to actually directly measure what does it mean to be in a flow state for a programmer. But much of my motivation for kind of going into that detail of all those brain studies is just to show how complex that is, right? There is lots of things you have to do. So much of my research right now is looking at what are some lighter weight things that we can do to get the same type of results. So one classic example of a metric people are interested in is this idea of cognitive load, right? So it's this idea of like how much things do people need to put in their mind in order to reason about something. What I'm showing right here is a graph of a programmer. Each dot is a method, and each kind of line is a connection. That means they've had to like work between those things. So basically what you see is this is one program over a month that represents how much knowledge they had to kind of encode just to work on that one code base. This is the type of cognitive load they may be potentially having, right? And we want to be able to ask questions about what helps reduce these sort of cognitive loads. And so there's actually lots of literature on other ways that you can measure cognitive load without having to go to an fMRI scanner. So one example is pupillometry. And what we can do here is there's actually studies that show as you become more engaged, your pupil size increases, right? And you can do, for example, a classic experiment is you ask people to multiply different numbers. And if you have simple numbers to multiply, 5 times 8, then it's pretty easy. But if you ask like 55 times 27, you're like, ugh. It's a little bit harder, right? And you can actually see the pupil size dilate more in response to that, right? So you get these really fine-grained controls for seeing how much load people have in a really small time span. So this is something people have done. So you just see an example of that here. Someone's pupil dilating. And this is already in slow motion because this thing happens really fast, right? Another thing that typically happens are people have these very fast saccade movements. So your eyes are constantly moving all over the place, right? We have the ability to know when someone is more focused on something basically on looking at their saccade patterns, right? So saccade patterns tend to be more localized when you're focused, but if you're going all over the place, you tend to be seeking something or confused. So this is yet another pattern that we can look. Turns out blinking is very interesting. We can use blinks to measure someone's focus level. The nice thing about blinks is it's a very easy signal to get. You can get it with a webcam, you can get it with a really cheap eye tracker, you can get it from someone watching you if you really want to. You can get it from wearing EEG because you can see the muscles activate. But basically, people only need to blink every 15 seconds, right? So basically, the eye area, all the, like your coding will start to deteriorate after 15 seconds. So you need to blink at least 4 times a minute, right? But people don't do that. They blink closer to like 15 times a minute, right? People blink as much as like, I think they, I want to say like hundreds of times. In certain cases, they tend to be mental disorders or very high stress. So basically, we can see when people are blinking out of the range or when they're blinking within what's more indicative of a concentrated, when they're more focused on something, right? Another interesting signal is looking away. So this is especially true when you're talking to someone. It kind of happens when, it less happens when you're looking at a computer, but if I'm in a conversation with you and I ask you to recall the last time you ate at a certain restaurant, and then you would kind of like look up and like, right? So this act of like, you kind of look up, it kind of helps you do that recall, right? There's lots of explanations for why, but this is something very easy to pick up. You can pick this up with the camera very easily. And this becomes an event for when do people need to look up information, right? That could become a signal for mental load. Body posture is another interesting thing. So when people are concentrated, when they're leaning back, there's these, they call butt sensors. So they look at your chair and they see how much you're leaning in or how much you're leaning back. And that has a lot to do with concentration, focus, etc. Facial expression tells you a lot about if you're angry, frustrated, you're happy, right? So there's lots of ways to do that. Then you can start getting into kind of more lower level processes. So you can measure the temperature of your skin, your heart rate, how much you're sweating, right? So if you sweat more, you tend to be more stressed, more engaged. And you can measure that by just the changes in conductivity of your skin. So there's sensors now, consumer products that do all these sort of things, right? And they have these ways of being able to hopefully identify these different states, right? The accuracy of these things is questionable, but if you actually combine a lot of these techniques together, they actually could be fairly accurate. Another technique I've looked at is subvocalization. So if you've ever read something, you ever notice that you kind of read it in your head, right? That's silent reading, but sometimes you do a little bit more than that. You move your lips. Right? So it used to be that back in the day, people didn't actually know how to read silently. They just read aloud, right? And it was the very first, I think it was St. Augustine, was the very first person on record to ever read silently to himself. And so there was actually this neat passage about someone writing this along. It's like his eyes just glided along the paper and yet his lips did not move, right? This was astounding that people could do this, right? It turns out that there's lots of reasons why people want to talk when they're reading. And mainly it's because when you're reading something, you're still priming your speech areas to be like you're gonna say it, but you don't fully do it. So you tend to prime your premotor areas, not your actual motor areas. So it basically tells your muscles to get ready. So you send these signals to the larynx and your lips and your tongue to kind of move, but you have this other thing that's saying, well, but don't actually, right? So there's other thing that we've learned to do that suppresses you from actually doing the movement. The thing is, that signal is still being sent, and you can measure this. And so people have actually used this to decode words people are saying. So they actually have silent speech recognition that you can do. They often do this in noisy environments where you can't use a microphone. So that's one technique. But it's the reason people sub-vocalize is often because of memory load. right? So there's studies that show, if you ever seen a speed reader, and all these books that say, they say to suppress subvocalization, and it's true, you can read faster, but what tends to happen is you don't recall it as well, you don't learn it as well, you just basically do lower on scores. So when they do students and they train them to subvocalize versus not, to suppress it, they can actually see that people don't understand the text as well. So basically what's happening is, as you're saying these words kind of to yourself, you're activating multiple parts of your brain that make that memory more interesting, right? So the visual part of it, the vocal part of you saying it, the combination of that together causes you to, basically your hippocampus says, well, two things are interesting in this. This is an interesting memory. Yes, we're gonna say this, right? And we've been able to use this to see when programmers are more likely to subvocalize during their task. And it basically gives us a sense of which programming activities cause the most cognitive load, right? So this is interesting because you could just do this with pretty cheap muscle sensors, right? Just one application of this. Some people, I just want to give you an example of a research paper. Some people have been trying to tell the difference when someone was struck and frustrated and in the flow state, right? So they just wanted to be able to know that. And they did this nice study of where they looked at all these things together. And we're just basically using a machine learning algorithm to be able to see the difference between the state of someone having high emotion and someone making good progress, right? And we're getting there, so we're starting to get better than a coin toss, right? So there's more work here. I think most techniques can get from 70 to 90, depending on the task and what you're doing. But we're getting to the point of where we could start reliably predicting what emotional or affective state you're in. So for the rest of the talk, I want to just talk about some basic applications for all these things. So I kind of laid out some problems that we're looking at, some studies there, some of the kind of techniques, but what can we do with all these things, right? So actually, we've been working on some lots of neat things. So I want to give you the craziest one. This one actually works. So one of the devices you can do is you can actually use a very large magnet to induce a current in your brain and basically do crazy stuff, right? You could do stuff where you actually turn off your ability to speak or see things. But you can also enhance things, right? So you can enhance your ability to do math. You can enhance your motivation on a task. So you could get to this point, and there's actually devices that do it. I don't know how safe they are. There's little devices you wear on your head, and you push a button, and it basically zaps your brain and says you're more motivated now. Because essentially what they're doing is they're kind of tapping into those neural circuits to increase your dopamine levels, which increases your pool of motivation. And okay, that's one thing you can do. The thing people do nowadays is they wait to the last minute. Why do you wait to the last minute? Because cortisol, stress, causes you to be motivated. And so you could work on something for 4 days, 2 hours at a time, or you could work on one thing 8 hours the night before it's due, and that stress will allow you to do that, right? That's why people work at the last minute. That's maybe why procrastination is good. You have less interruptions. You didn't have 4 segments of doing things. Well, maybe you can do motivation buttons instead. You see this little light here? All right, so let me give you a short demo of this. So back when I told you my biggest problem was fragmentation, I found that I quickly only had about a minute to do anything. And what I was doing was I was like, well, not a minute, 30 minutes. What I was doing was I said, I have 30 minutes to prepare my slides for class, right? That's all, because class starts in 30 minutes, right? So let me do that. But if I were to just work on it without any kind of guidance, it would be like 5 minutes left. I'm still on slide 2 because I was messing with that diagram I wanted to perfect. Crap, I don't have slides for class, right? You don't want to be in that situation. So what would happen is I would start listening to music that was 30 minutes long. It was like a playlist, kind of when you go running. So 6 songs, you know, if you're on the 3rd or 4th one, you need to start wrapping it up, right? But after a year of listening to the same music, it kind of started going insane. So what I developed instead was a light, kind of using a green light, red light, green, yellow, red light metaphor that would help you track where you are. And so this thing would let you see when you basically, when I'm in yellow, I mean to stop. When this flashes a police light, that means I'm done, right? And what would happen is I would notice if I use this light, it was a great replacement to using music. It was just as good as being able to time box my stuff. And it was better than setting a Pomodoro timer because those were just alert, like you just are interrupted. You're like, you're done, right? So it wasn't really any better at helping me pace myself. So this allowed me to time box. And what's neat is light is a signal that you process at a much lower level than, say, looking at your clock or thinking about things. If you say I have 20 minutes to do something, and you have to subtract it out from the time based on when you started and remembered, that's a lot of mental operations you have to do every time you want to check on the status of something, right? You can have other kind of physical movement. That's probably just as good as light. But in a cafe and stuff, that seems to be more drowned out. Light just seems to be the strongest signal still, right? So I've been using this for almost a year now, and it's great. I love that I can use this time box stuff, right? And you could see for using it for talks, I could say, I'm in red light, I want to be by a certain point. I wanted to be in applications by that, right? Okay? So what we want to do now is we want to know, okay, we kind of built this tool based on intuition. How can we know that it's actually better than regular time boxing and stuff like that? So we want to start measuring different things like the stress level. So there's one thing about being confronted with the light is red. Oh my God, it's red. I need to do something that does cause more stress. I think that you can kind of overcome it, but I want to know, like, if say I gave two people a programming task and they had to kind of do it based on completeness, someone without any guidance might focus getting stuck on one area and not kind of do the complete part, right? You need to do 10 things, right? It doesn't matter the quality, just do all 10 things, right? It may be if you gave this light time boxing to a student that they would be more likely to do all those things. But we want to also know there's different types of patterns that we can do, right? So if you just do an intermittent reminder that, hey, look, you're in yellow state right now, and that only came up every couple of minutes, you might think differently, right? So that's one thing we're looking at. Another thing we're looking at is mood lights. So we're deriving all the data that we have about people to know whether you're frustrated or in the zone and that sort of stuff. And we're using all this analysis to basically, if you look at, say, the past, say, a 30-minute window, and you look at your kind of your blink rates and your GSR levels and stuff like that, if it's above a certain threshold, then we color that box. And if after a certain window of time you have enough boxes kind of colored in, and this is a moving window, what's considered you in the zone, right? And so in our prototypes, this seems to actually be a really good thing. It seems to work pretty well. So this is pretty promising. So some people have actually used this to prevent interruptions to them. So they would actually have lights like this in their office. And there's actually been field studies where they use these lights to kind of ask someone not to interrupt them because they're in red, which means don't bother me right now. Another application we're looking at is this idea in remote technical interviews. So if you ever go on an interview, it could be very stressful. And the worst part, especially on even a whiteboard situation, someone is asking you, can you please make a, do a red-black tree and delete a node? Like, oh God, okay, I did that 5 years ago in my class. But you start doing it on the whiteboard and like, what are you thinking now? You're like, I'm trying to solve it, right? And it's like this incredibly disruptive, it's the worst possible way to figure out anything about if someone's good or not, right? Remote technical interviews have similar problems because you basically ask the code in a terminal and then someone can't even see you and they're just asking you questions. What are you doing now? Why did you do that? And they just keep interrupting you. So we want to test if we can create a better mechanism for this where we basically have a remote focus light where you can see that someone is cognitively engaged right now. Can you please wait a couple minutes or a couple seconds before asking them something so that they can have a better sense on when to do that. So better technical interviewers already do this. They will always say, okay, I told you the problem. I'm gonna walk away from the phone and give you 5 minutes to just think about this, right? So some people do that and they kind of build it in, but a lot of people don't. They don't know how to do that and they don't know how to sense when is too busy. Another thing we want to check out is this idea of blackout interfaces. So this idea of someone can see you in real time doing stuff creates this extra level of stress. And we want to see if you had this idea of a blackout time, of where you can kind of explore and test things out in a certain window of time, say like a 3-minute time, where you're blacked out, and then it came back on. And then someone can ask you then that, okay, you know every 3 minutes your blackout's gonna go out, and someone can ask, okay, what did you do those 3 minutes? Can you explain it? Our idea is that this would help people have less stress, and they would have better ways of kind of coordinating when they have high cognitive load or not, and do better on interviews if we had that sort of mechanism, right? If we blacked out the interviewer. So the nice thing about these biometrics is it allows us to actually test that. Fundamentally, is someone less stressed when they have this mechanism or not? Because we could say, well, they scored 5 points better on the exam, but it doesn't really tell us why. The biometrics lets us see why, right? Another thing we want to look at is inspired by what game developers often do. So when they design levels, they often will kind of do metrics where they'll say, where do people die on a map, right? And they'll look for like, well, everyone always dies like when they run around this corner and get shot, or like this ghost comes or whatever. And it's really unfair, people are mad. And so what they try doing is they try analyzing that and seeing how can we improve this data. We want to do the same thing with APIs, right? So if you took, say, the Android API, where you're developing apps, and it turns out you're really frustrated every time you're working with this one class library, and this is not just you, but everyone else, then that might be a good feedback to the stakeholders that lots of people are having trouble here, right? So in some other work we've done, we've actually built a fatigue detector, so we could tell when you're fatigued. So we tried starting out with some basic stuff like, do you hit backspace more often? Do you have lower quality code based on some metrics? But it turns out there's something really simple that predicts fatigue really well. And you wouldn't believe how easy it is. It's the time you hold on to the key and time in between key presses. And the reason why, lots of reasons why. Basically your motor response is slower when you're fatigued. So you tend to have slower, so really energized and then slower, right? But there's others. You tend to have more kind of brain parts that you're like, control, what am I doing again? Like you kind of black out more. And so you have these like long delays between like key presses because you're trying to do a more complex keyboard operation, right? Those two things together predict fatigue really well. So if you had such a thing, and you don't even need biosensors, right? You could just do it on instrumentation data. You can ask questions about, well, this programmer just worked on this piece of code. It's related to security and our product that 98% of our revenue comes through. And they were really tired, and there was a lot of cognitive load when they were doing their task. You might want to review that one more. Like versus another commit that came in, they seemed to be energized. It was a low cognitive load task. Maybe we won't review that one, right? Because the problem with code reviews is if you review everything, then you review nothing. Because if you look at code reviews in practice, most people don't actually find bugs because they're just, like literally if you go to Microsoft and see their code review, they're like, yep, this looks good. And they're done, right? They try getting these over as soon as possible. But if you try limiting these to real important use cases and you had a way of telling you that, then you can flag these things for review. So there's recent work where people have been looking at the difference between experts and novices, and kind of back to that golf thing I gave you. This is maybe controversial, but this idea of a sorting hat. You said you have 5 years of SQL experience, and okay, but you sit on the sorting hat, and it seems you only know about the typical 1 year expertise, right? You know, so we're doing this with like undergrads, and you could see like, you know, first to senior, and you could predict which one they are based on their brain signals. And it's all about that expertise model, right? Experts should exhibit less brain activity as they do things that you're supposed to be better at. And if they're not an expert, or at least not at the same level as where they're expected to be with their peers. So you could start doing things like that. Maybe a little scary, but okay. You can start optimizing your flow. You could try, you know, so there's tools like Coda-like that tried looking at your flow. So there might be, similar to that recommendation thing we talked about, here's are ways that you might be able to stay in flow better, right? Really abstract, but. And I wanted to show you something really crazy just to end with. So other work that we've done is we've looked at coding in virtual reality. So you could actually see through your hands with the mounted camera. You could use a leap motion to edit stuff. So we're actually building, basically what this developer is doing is they're building a system that looks to live tweets and will fly around and land on a cherry blossom tree, right? And they're doing this in pretty much real time, right? So this is all in the Oculus Rift headset. I'm trying to see some of the stuff they're doing. There's the tweets flying around. They kind of look around and see all this sort of stuff, right? They did this entirely in virtual reality. The amount of affordances that you get in there are pretty crazy. But what's the connection with this? The music's kind of nice to have in the background. Kind of my vision where I see a new class of software developers coming from is it was inspired when I saw how Watson works, right? So Watson doesn't work because there is all this cool AI or new algorithms. It's all the data. They literally had just people do all this data engineering, not software engineering, right? They basically took data sets, they massaged it, they fed it slowly like a baby would eat some food so it learned how to do stuff. When it made mistakes, it kind of fixed it up and it patched it until it got really, really good, right? That's how Watson was created. There's no smarts to it at all. It's all the smart data training. Who trains that? Who are those people? Those are software trainers, right? So the way we will be building software in the future isn't that you're designing it explicitly like my car is gonna look for this signal and then it's gonna turn left there. It's gonna be all trained with real world examples using machine learning algorithms, and you're gonna be guiding them to doing the right thing. How are you gonna be guiding it? You're gonna be interacting more directly with a simulation of how the software works, right? So one thing that we've been building is this interactive machine learning algorithm that we're starting with classifying. But basically, you know Fruit Ninja, right? Where you slice through with your Connect and you chop all these things. We're doing this with data. So we have a human that comes in and they can kind of visualize the different data points and they slice it and they give it to a machine learning algorithm and they kind of learn some parts of it and then they train more data and give it to it and train it. And then it's an interactive process of where they're able to essentially build something that's smarter than what the machine learning algorithm can do on their own. Why? Because parameterization is usually a problem. So you don't know what type of kernel to select, for example. Should it be a linear, polynomial, a sphere? The human is better at selecting those sort of things. And they can do that in real time by getting feedback and seeing what it does, like what examples is it failing on. And where I see biometrics fitting in this is it's gonna become a whole other modality of input, right? So if I'm saying like, you're doing that wrong, that's not something I need to express by typing you're doing this wrong. It's something that's gonna be directly sensed, right? So you're gonna start having all these other inputs, whether they're artistic, emotional affect, whether they're combined with motion or not, is gonna become one unified way of inputting and training programs. So that's where I see this going in the future. That's where the bionic part of the talk comes in, right? But with that, I just end it with questions from the audience.